Alrighty, here is number 4 from the complex kinematics worksheet. A robber is planning a getaway on a freight train. The train travels at a constant speed of 7 meters per second. Right as an empty boxcar passes the train, the robber starts running from rest to catch the train. He accelerates at a rate of 3 meters per second squared until he reaches a maximum speed of 9 meters per second. He then moves at a constant velocity until he catches up with the train. How far does he need to run to catch the train? So there is a little bit going on here. We've got two objects that we're dealing with, a train and a robber. So let's draw both. Here's our train moving at a constant velocity. So the train's going the whole time at the same speed. And then here's the robber. Make him look like a little bandit. Starting from rest, accelerating to whatever his speed is, I think 9 meters per second, and then maintaining that constant speed until he catches the train. We're going to break this up into part 1, when the robber is accelerating, and part 2, when the robber is moving at constant speed. So this scenario is similar to the cheetah problem in that the object is doing two different things, but this is a little bit more complex. Let's start with what we're given. And I'm going to list a given for part 1 and part 2. So given, let's say for part 1. We know that the velocity of the train the whole time is the same. So v for the train is 7 meters per second. That's going to be the same for part 2. We know that for the robber, v initial, I'll call that r, is 0 meters per second. He's starting from rest. We know that the v final for the robber is 9 meters per second. And we know that the acceleration for the robber is 3 meters per second squared. Train has no acceleration, again, because it's constant velocity. In part 1, there are two things we want to find. First, how far does he go? Second, how long does it take? So I'll call that T1 robber, and we'll call this delta X1 for the robber. Part 2. Again, I'm going to just put the train's velocity in here because it's the same, 7 meters per second. We know that for part 2, the robber is moving at a constant speed of 9 meters per second. I forgot to write the word given, I'm sorry. What do we want to find for part 2? Delta X2 for the robber. Because in general, what we're looking for is how far the robber ran the whole time. So what do we know is the same? We know that the robber and the train are going to be in the same place at the same time in the end. So we also know that how far they travel total from the time the robber sees the train and starts running until he catches the train will be the same. So let's look at the robber for part 1. So part 1, robber. We know his initial velocity, we know his final velocity, we know his acceleration. So for part 1 in the robber, we can use the no time equation to figure out delta x. V final squared equals V initial squared plus 2a delta x. He starts from rest. V final squared over 2a equals delta x. So this is 9 meters per second squared divided by 2 times 3 meters per second squared equals delta x. 81 divided by 6 gives me 13.5 meters for the distance the robber travels in that first part. So this is delta x1 robber. We need to figure out how long this takes him. So again, you have an option for equations that you want to use. I'm going to choose v final equals v initial plus at. A is 0. So v final over a is the time it takes the robber to run that long. 9 meters per second over 3 meters per second squared equals t. So it takes 3 seconds for the robber to run 13.5 meters. Now let's look at the robber for part 2. In part 2, the robber is running at a constant velocity, so we can go back to our old equation of v equals delta x over t. So delta x for part 2 of the robber is going to equal the velocity of the robber times the time. We also want to look at the total motion of the robber. We know that he's doing 2 different things. So he's accelerating in part 1, he's moving at a constant velocity in part 2. But we know that the total distance he covers, so delta x total, will be equal to delta x1 for the robber, which we just found, plus delta x2 for the robber. I already have over here delta x2 equaling the speed in part 2 times his time. So let's isolate this delta x2 for the robber right here. So this would equal delta x total minus delta x1 for the robber being delta x2 for the robber. And then set these equal to each other to see what we can eliminate. So in this case, we don't really care how far the robber went in part 2, so I'm going to get rid of it by making the substitution. Speed of the robber, and this is in part 2, times the time equals the total distance covered minus delta x from part 1. We know what that number is. We know what VR is, so let's put those numbers in. 9 meters per second t equals delta x total minus 13.5 meters. So I've gotten this down to 2 things that I don't know. I don't know the time, and I don't know the total distance covered. And let me actually add the subscripts up here. So this is the time for part 2, T2, 2, and 2. For the robber, I also know that the total time is equal to his time plus in part 1 plus his time in part 2. So the total time minus the time in part 1 will give me his time in part 2. My end goal is to get this in terms of x total and t total, so I'm going to substitute in t total minus t1 in for t2. This leaves me with 9 meters per second times t total minus t1 equals x total minus 13.5 meters. We know that t1 was 3 seconds, so 9 meters per second t total, so this was 3 seconds from part 1, minus 9 times 3 is 27 meters equals delta x total minus 13.5 meters. We now have x total and t total, so I'm just going to isolate x total so it's all by itself. Delta x total equals 9 meters per second t total minus 27 meters plus 13.5 meters. So delta x total equals 9 meters per second t total minus 13.5 meters. X total in terms of t total, so this is the total distance covered divided by the total time that this takes. We eliminated the fact that the robber had the part 1 and the part 2, and now we're just looking at the whole picture. So it's time to look at the train, because the train is the same the entire time. So the total distance covered by the train is equal to the total distance covered by the robber. It's also equal to the constant velocity of the train, so Vt, which is the same as V total, times the total time. Delta x total equals this. Delta x total also equals this. So for the train, we're going to set these equal to each other. Velocity of the train times the total time equals 9 meters per second. Total time minus 13.5 meters. 7 meters per second, that was Vt. Total time equals 9 meters per second. Total time minus 13.5 meters. Solving for total time, we get negative 2 meters per second, tt, equals negative 13.5 meters. So the total time equals 6.75 seconds. The only thing left to do is solve for x total. So x total equals constant speed of the train, 7 meters per second, times total time it took, 6.75 seconds. These two multiplied together give me 47.25 meters. So the total distance with one sig fig is approximately 50 meters. Again, this problem is a substitution. It became more complicated by the fact that instead of being constant velocity the whole time, we had an accelerating part and then a constant part. But once we broke it down, eliminating the two parts from the robber by getting the two equations, two unknowns, this became just like one of our old problems with the substitutions.